Welcome to the show, everyone. I'm Simon Carver, and joining me from his backyard shed in Sydney is Lachlan Reid. Lachlan, I want to kick off today's episode with a number that genuinely stopped me in my tracks. 20,000 gigabytes per second.
20,000 gigs a second? Far out, Simon. That's not just fast, that's like trying to drink from a fire hose that's hooked up to an ocean. What is that, some supercomputer's internal cache?
It is actually the GPU-side linear processing bandwidth measured in a recent offloading study. It represents how fast a modern high-end graphics chip can access its local high-bandwidth memory. But here is the kicker: the absolute brutal contrast. Host device I/O, meaning the connection between that fast chip and the rest of the system over PCIe, was measured in that same study at a mere 25 gigabytes per second.
25 gigs versus 20,000? That's a classic bottleneck right there. It's like having a Ferrari engine, but trying to feed it fuel through a coffee stirrer.
Exactly. And this is the core reason why running massive, dense GPT-3 class models on an ordinary iPhone isn't actually a problem of raw compute power. It's not about the FLOPS. It is a hard, physical limitation of memory bandwidth. When you run dense autoregressive transformers, every single generated token requires touching practically every single model weight and KV cache state.
Right. So if you're trying to stream those model weights weight by weight over the bus for every single bloomin' token, you are dead in the water. That constant data shuffling is what absolutely butchers your battery life and sends latency through the roof. It's a physical dead end.
It really is. If you've got a dense model with over 100 billion parameters, you can't just page those weights from your storage or stream them over a network block by block on the fly. It's why systems research papers like flash attention and paged attention are so obsessed with I/O-aware operations. They are trying to minimize the amount of times we have to touch memory, because memory movement is where the real tax is paid.
Spot on. It's not the math that's killing us. It's the logistics of moving the numbers to the processor. So, if we can't fit the giant brain on the phone, and we can't stream the brain's weights token by token, how on earth do we get GPT-3 class smarts on a device without just relying on a standard expensive cloud API?
That is where we have to completely flip the paradigm. Instead of treating the network as a pipeline to a remote cloud GPU, what if we treat the internet as a sparse, typed, and verifiable memory layer?
An external memory layer? Okay, wait a sec. So we aren't sending our prompt to some massive server to do all the thinking. Instead, we keep a small zippy model on the phone, say 0.5 to 3 billion parameters, and use the network to fetch specific intelligence artifacts as we need them?
Precisely. We challenge the fundamental assumption that all knowledge has to live inside static, frozen neural weights. If you look at research like that's retrieval enhanced transformer, they showed you can get performance comparable to a massive model like GPT-3 while using a fraction of the parameters, simply by retrieving from an external database of trillions of tokens.
Yeah, and KNN-LM did something similar for Perplexity without even needing retraining, just using nearest neighbor lookups over external data. It's like having a smaller local brain that knows exactly how to look things up in a giant library, rather than trying to memorize the whole library.
Yes! And it gets even better when we talk about intermediate states. Papers like Prompt Cache, CacheGen, and CacheCraft show we can reuse or compress KV caches across different prompts instead of recalculating them from raw text. The local model acts as a smart router and parser. It handles the interface, the local tools, the private personal context, and only pulls in highly reusable, content-address states when necessary.
It's like downloading pre-baked chunks of understanding. But to pull this off, the network transfers have to be tiny. If we go back to the math, if you're fetching multi-megabyte objects per token, the latency is still going to be garbage, even on a fast connection.
Oh, absolutely. The math is relentless here. Let's say you're on a standard broadband connection at 200 megabits per second. If your fetched artifact size is around 256 kilobytes per token, you can plausibly hit 97 token equivalents per second. But if your artifact size balloons to 8 megabytes per token, that same connection drops you to a pathetic 3 tokens per second.
3 tokens a second is agonizing. That's like watching paint dry. So the key is keeping those fetched artifacts strictly sub-megabyte. You want to fetch compact typed artifacts like specific KV chunks, proofs, semantic deltas, or sparse expert pages.
And that's where alternative sequence architectures like Mamba come into play. Mamba scales linearly and maintains a constant size recurrent state, avoiding the massive, growing KV cache of standard transformers. That makes it an incredibly promising candidate for a local edge core.
All right, so how do we actually build this thing without turning it into a massive, fragile research project? The protocol design report suggests a hybrid called CORTEX IP-Lite.
Right, the light part is crucial here. Instead of trying to build a fully decentralized, public, peer-to-peer swarm using something like IPFS, which introduces massive lookup latency, privacy leaks, and censorship risks, CORTEX IP-Lite is local first, but bootstrap assisted. It uses reliable low-latency CDN hosting for public shards, while keeping private personal data strictly on the device.
And the plumbing is built on QUIC and HTTP3, right? Which makes total sense because they give you multiplex streams out of the box. No head-of-line blocking. You can pull down a semantic shard on one stream, while a skill pack or a proof verification result streams in on another, all over a single connection.
Exactly. And the optimization of the system can be expressed beautifully through information theory. We want to minimize the conditional entropy of the answer given the query, the user's local state, and the retrieved artifacts. If we write it out, we are looking at h of the answer given the query, user state, retrieved shards, skill outputs, and verifier constraints.
I love that. By feeding the local model high-quality, pre-computed context, you're literally reducing the amount of uncertainty it has to resolve. You are shrinking that entropy. But how do we handle long, ongoing conversations without resending the whole transcript every single time?
That is where the semantic delta context protocol comes in. Instead of replaying the entire history, we treat the conversation state as a dynamic graph. When new events occur, we only transmit the delta entropy. The communication cost scales proportionally to the delta entropy between the current state st and the previous state st-1, rather than scaling linearly with the entire transcript length O of t.
That is a massive win. You're basically patching the local brain's memory state on the fly. So what's the game plan to actually build and test this setup?
The paper outlines a very pragmatic 4-phase roadmap. Phase 1 is all about building a CPU-first desktop simulation twin, along with a simple iPhone client stub to test the content-addressed object store over HTTP3. No fancy models yet, just setting up the transport plumbing.
Right. Get the pipes working first. Then Phase 2 brings in the neural state reuse protocol. You implement the prompt module and chunk cache reuse. That's your first major milestone, where you benchmark and prove you can get those real-world TTFT reductions, like the 1.5 to 10 times speedups reported in the prompt cache paper.
Then in Phase 3, you add the sandboxed skill runtime, things like local math solvers, code execution, and verifiers. And finally, Phase 4 is the Holy Grail, integrating the persistent worldline store, enabling semantic delta sync, and running a live pilot on a physical iPhone.
It's a solid, step-by-step ladder. Don't try to build the whole world at once. Start with the transport, prove the state reuse, add the skills, and then wrap it in the personal context.
Exactly. It moves us away from trying to brute force bigger and bigger models onto mobile hardware, and instead shows us how to build a highly efficient, highly collaborative network protocol for intelligence. And that is a fascinating place to leave things. That's our show for today. I'm Simon Carver.
And I'm Lachlan Reed. See you next time, guys. Cheers.